also thank the organizers, of course, for giving me the chance to come and present our work. So we are doing a theoretical analysis of materials, and especially these copper-based chalcogenides. And the outline will be, first I will show some latest results that we have on CZTS, and then going for, which was the original thought here, was to going for materials towards ultrathin photovoltaics. But first, a little bit about the latest result. And CIGS and CZTS, we know for sure. We had a really good talk by Susanne here. And she talked about this compensated defect, which is very important in the material. So we have this fully compensated or neutral defect, copper vacancy, zinc on copper. And we have the antizide pair, zinc on copper, copper zinc. These are fully compensated, neutral, defect, and not an, well, acceptor, donor, acceptor, and donor. So they're fully compensated and important in materials as well. What we found out, and this is a little bit a few years old result, but it's related to Susanne's talk here. Assume we have an A-type materials, so we have a copper poor material, A-type material. If you have a copper poor material, we believe that the band gap should increase because we have copper vacancies. However, if we have this copper poor defect, that will also induce more of the antizide pairs. The formation energy for the antizide pair is very low as it is, 0.3 eV, 0.4 eV, something like that. But if you already have a copper poor materials, this formation energy of antizide pair becomes even lower. So the copper poor defect induces the antizide pair formation. And the antizide pair formation has a lower band gap, which means that it a little bit stabilize the band gap. And the reason why this defect induces antizide pair is that it actually formed then a line of an acceptor, donor. And if you look at the octet rule, you will see also that it is a little bit can explain why it's more favorable to have an antizide pair when you already have another defect. Oops. So that is a little bit old result, but this is a new result that we have here. And that is about if you have oxygen in the samples. If you have oxygen in the grain boundaries or oxygen at the surface, it's a little bit less studied, but we have experimental also started to look at it, but theoretical we're also trying to support what's happening. And assume that you have oxygen, and we believe it goes to the sulfur site, because then it is isovalent or isoelectric. So it should not do much to the material. It little bit breaks up the bonds here, so it is having a deformation of the structure because it's so much smaller atom compared to sulfur. But it doesn't do that much to the material. And we also know that in CZTS we have a lot of sodium in the material. And sodium can go interstitial, but it also goes to the copper site. And here we're only showing for the copper site. So if sodium go to copper, again, it is an isovalent defect, not a donor, not an acceptor. It should be neutral, so to speak, electronically. And it doesn't do much to the material. But what we see is that there's a strong binding energy between sodium and copper and oxygen and sulfur. Sodium will go to the next nearest the nearest neighbor. It will actually go here and form a quite strong bond to the oxygen. The binding energy is 0.8 eV, which is a little bit surprisingly strong bond, considering that this is isovalent dopants. This is what also the experimentalists see when they do the SIMS. We see a clear correlation between the oxygen signal and the sodium signal here. So, but here the explanation for the binding is different from the other copper antizide pairs. Here it is the electronegativity from sodium, which is much smaller than copper, and oxygen have high electronegativity compared to sulfur. So sodium and oxygen prefers to be close to each other, forming a small ionic bond. Well, most of it is covalent, but it also have a little small ionic character. So that was a little bit the latest result we had on defects in this material. So I will go over for the second part of the talk. So going for ultra-thin photovoltaics, ultra-thin films. And the motivation for this is that we want to have ultra-thin film, which we define here as something between 10 and 100 nanometers. We want to have it because we want to have lower material usage and weight, so it's lower cost. Shorter path for the carriers, but the requirement is that we need a high absorption of the materials here. And of course, then we have all other properties that the materials should be stable and no defects and so on. But this talk here will only be about trying to see what should be the material property to have to go for ultra-thin material. We will not go for stability of material so much in this talk. We will start from what we know already, CIGS and CZTS, but we will replace some of the anions with other atoms to try to analyze different types of copper-based materials. So, for instance, we are replacing zinc here with some group elements, many different elements here. But we can also replace it with some group 4 element or some group 5 element with different phase. We'll go through different structures, of course, because different materials, compounds have different structures and phases, and we'll go through a few different structures also. The problem when we go for ultra-thin film is, of course, that the absorption, if you have a thick film, much of the light will be absorbed, but if you have thinner and thinner film, less and less will be absorbed and reflected or transmitted instead. And the total absorbance goes exponential with absorption coefficient, the material property, times the thickness. So if we make half the thickness size, then the absorption has to be twice as much, twice as high. So we have to have a much better absorbing materials in order to do the same efficiency for the material. We calculate the efficiency of the material, not really the device, but the efficiency of the materials by the Shockley's ideal diode equation. And we have the current density, generated current density, which more or less depends on how much is absorbed, which depends on of course, the absorption coefficient, how good it is to absorb the material. And then we have the recombination current, which can both be radiative and non-radiative. And the radiative is the black body radiation merely, and again, it is how good it is to absorb or recombine the light. And then we have the non-radiative, and here we're looking at the Auger effect. We are not looking at defect-related recombination because we are looking at the maximum efficiency of the material and not so much about, well, assume you have a very low concentration of defects then. The maximum efficiency as a function of thickness of the materials, if it is thick enough, it will absorb all light, and then we have the SQ limit of roughly 32–33% if we have a band gap of around 1.4 V. So that is the normal maximum efficiency. If you go for thinner and thinner films, it's more or less keep its efficiency until roughly 500 nanometer thickness, whereas drop drastically. And what we want to find is a material where the efficiency keep maximum efficiency also below, well, 100 to 300 nanometer here. So how should that type of material look like? Well, the absorption coefficient for this is CZTS. It has normally a square root-like behavior at the onset, but then it has a strong peak at the absorption coming from the Brillouin zone edge, or the von Hoff singularities, where you have strong absorption. So that is quite characteristic for many materials. And the question is a little bit, how should this absorption curve look like in order to have a good efficiency for ultra-thin materials? Should one look at how the solar cell spectra look like, or how should that look? Or how should the absorption be in the material? How should the absorption coefficient be for most efficient materials? So we can a little bit simulate where this peak shall be in the absorption spectra. And what we find is that, that the absorption, if it is, this peak is close to the onset, then we can keep the efficiency also going down to 200 nanometers or even below, and keep high efficiency. So we are looking for some materials that have high absorption at the very band edges. And of course, such material should have very flat conduction and valence band. It should be very flat, because then you have a high joint density of state, and you will have a lot of absorption, high absorption at the very band gap energy. The problem with such material is that flat bands mean high effective mass, which is then not a good property for the materials. So that's the disadvantage. You will have a high absorption, but the transport properties will be less good. So maybe it should be look like this instead. Maybe it should have some channel where the electron, with small effective mass, where the electron can easily transport away from the material, but then you should have flat bands, and well, maybe it should be flat bands here, but maybe also a channel for the holes here. That could be maybe one way to create materials for ultra-thin solar cells. But we a little bit suggest that it should look like this instead. We should make use of multi-value engineering. We should have flat bands, but we should have maximum and minimum, direct gap preferable, and at valence away from the gamma point. So you should have several values, which then create a large joint density of states and strong absorption from different values now. And this is a little bit related to what people are talking about when talking about thermoelectric materials. They're also going for multi-value band edges. Another thing that is that one have to consider if going for thinner and thinner film is what the band gap should be for such thin film. We know that the band gap for PN junction solar cell should be 0.3, 0.4, 0.5 EV in order to have a maximum efficiency. But that derivation is for a thick film. So how is it the same for thinner and thinner films? No, actually not. If you go for ultra-thin films, the maximum, maximum efficiency reach for lower gap, band gap. So if we go for ultra-thin films, we maybe have to look for materials with a little bit smaller band gap energy. So some results now from all these different copper-based materials. We have this, the regular CZTS and CIGS, CGS, and some of these alloys also. So CZTS like materials. The absorption coefficient as function of the energy, energy minus the band gap, so we can compare the onset to absorption here, because it's very important to have strong absorption near the band gap onset, band gap energy. Sorry. The regular traditional materials, but then we're also looking for when we are replacing zinc with different group 2 elements. And we see some materials have a little bit better absorption on the onset here, but it is roughly the same absorption for these materials. Going for copper group 4 compounds, little bit better absorption here for some of the materials, especially copper silicon. Here. But if you go now to copper group 5 compounds, then we see a clear improvement of the absorption near the band gap energy. Of course, these materials, as I a little bit said in the beginning of the talk, that these materials, the quality when they're growing this type of materials, copper bismuth, copper antimony sulfide, the quality of the material is not good today. But if one can grow very good quality materials of this one, it will have very strong absorption near the band gap energy. And the reason why it has so strong and very good absorption is that if you compare to CZTS, these copper bismuth phases have very flat valence band, but it also very flat conduction band. And the flat conduction band originates from the bismuth or the antimony P states. So we know that this bismuth and antimony, very often those compounds have a flat conduction band. And also it has several valleys, so it is a multi-valley band gap materials. Copper group 4 compounds has flat valence band, which is then very good, but the conduction band is has a stronger dispersion, so you don't have that strong absorption. You have a little bit better absorption, but not as good as for the copper group 5 compounds. And that is now seen directly in the efficiency versus thickness. The traditional materials, of course, it's very much depend on what band gap it has from the beginning, and because the band gap defines the efficiency for thick films. So one should maybe not look so much about the exact value for the different compounds here. What is more important is to see if it keeps its efficiency when you go for thinner and thinner films. Because the band gap we can normally improve by doing an isovalent alloying. We see here that some of the materials, actually CZTS has a quite good, stable efficiency when going for thinner films here. Going for the copper group 4, it doesn't improve that much. It's a little bit better than some of the materials. But if you, and also this replacing zinc with another group 2 element, some of the materials has improved efficiency, but not that much. But copper group 5 compounds, there you can see that it is a more stable efficiency when you go for thinner film thicknesses. For this copper bismuth and copper antimony compounds, we also can do the alloying, anion alloying, to optimize the best band gap for thinner and thinner films. So for each film thickness, we can optimize the band gap so we can get the highest maximum efficiency for that thickness. And looking at the absorption coefficients again for these alloys, copper bismuth sulfide selenide, compared to traditional gallium arsenide and CZTS, we see that the absorption coefficient is much, much higher than the traditional materials. 5-7 times better in this region. So that means that you can make the film 10 times thinner, having the same efficiency. And that is what we see here. For these optimized alloys, the efficiency can go, and you can have efficiency, maximum theoretical limit, of course, here, of 150 nanometers. So that is what you can reach if you manage to grow a high quality sample, of course. That's ideal sample. But that is a possibility at least. The problem with this material is that it is an indirect material. So it is a multi-valley band gap materials. but it has an indirect gap. So the efficiency I'm showing here is without the Auger effect. But if you now, since it is indirect materials, the Auger effect will play an important role, and that will lower the efficiency by some 5%. So that is killing a lot of the efficiency in the materials. The good thing, well, if you can talk about the good thing about the Auger effect, but the good thing is that the Auger effect just lower it rather constantly. It keeps the, if you look at how stable the efficiency is here with thickness, it's more, it has the same stability here. So even if it has lower efficiency for thick films, then it has lower than traditional materials. For thinner film, it has a higher coefficient compared to gallium arsenide and CZTS. So even, well, here you can have 25% for very thin films. Of course, we want to, the difference in the band gap, indirect and the direct band gap for these copper bismuth compounds, or copper antimony compounds, the difference between indirect and direct band gap is only 0.2 eV. So it is just a small difference there. If we can manage to make the material a little bit more direct, it doesn't have to be a direct material, but a little bit more direct. The difference between indirect and direct should be 50 MeV or something like that. Then we will come back to this efficiency again. So for us, theoreticians will think about how shall we make these indirect materials with Auger effect to become more a direct material, direct gap materials. And we have tried different things. We have tried straining a material. We are trying to, when we do the alloying, we are trying to doping the materials a little bit, but we have not found a good way until we come to that we will try to do the material amorphous. If you're making this copper bismuth, antimony also, but here we're showing for copper bismuth sulfide, if we manage to make this material an amorphous materials, it will go for more direct gap materials. And that is what we see for different other semiconductors. If you do it more amorphous, you will have a more direct gap type materials. So the absorption with the crystalline, which is red curve here, it has very low absorption in the beginning because it's indirect, but the amorphous material has an absorption directly at the band gap energy, since it is a direct materials. So here we have a way to actually to make these copper bismuth alloys as a direct gap material. Again, I want to say that this is pure theoretical values for ideal materials without the defect and with perfect crystallinity or perfect amorphous structure here. But the aim of this talk a little bit to say how shall a material look like in order to go for ultra-thin materials. Keep making use of the same p-n junction form devices that we already have for traditional thin film materials, and also to show how good can such material be. So coming to the summary, so it is possible to have a very high theoretical maximum efficiency for thicknesses lower than 100 nanometer. The requirement for such material is that it has to be high absorbing, it has to have a high absorption coefficient, especially at the band edge absorption near the band gap energy. That means that you need a large density of state, joint density of state. But we want to keep small electronic mass for that. And doing that, go in that direction, we believe that we should look at materials that has multi-valley band edges and making use of that you absorb also in different part of the brilliance zone of the material. For such material, it is important that, well, it's very easy that the material become indirect due to having band gaps in different places, not at the gamma point. So we have to be sure that it has a direct gap, or at least the difference between having a direct gap and indirect gap should be small. Roughly 50 MeV, then you the effect of Auger will be quite small. And also, if you go for ultra-thin films, the band gap, you should probably look for material that have a smaller band gap than you normally are thinking when you're looking at p-n junction solar cells. So by that, I want to thank the organizers again for inviting me to come here. But I also want to acknowledge my collaborator, Rong Sheng, who left the group, Konstia, which is coming as a new student, Sigbjörn, who is doing the experimental work at our collaborator partner, Dan Huang, who is working also in China now with the materials, and Sasha or Alexander, who is doing the amorphous materials. And also want to thank the collaborators I have had during the years when doing this work. So thank you very much.